Welcome to The Explainer. Today, we're diving straight into the foundational tools for thinking exactly like a computer. You know, before a programmer types a single line of actual code, they really have to map out their logic. Think of it like drawing the blueprints before building a house. So we're going to explore how flowcharts and pseudocode serve as these ultimate architectural plans, transforming your complex human ideas into instructions a machine can flawlessly execute. Let's get into it.
Here's the roadmap for this explainer. 1. Thinking like a computer. 2. Visualizing the program lifecycle. 3. Decisions and accumulators. 4. Writing logic with pseudocode. And 5. Testing through manual tracing.
Section 1. Thinking like a computer. So to really grasp programming, we first have to understand that computers, despite all their massive processing power, are completely literal. Programming is simply the act of giving step-by-step instructions in a language the machine actually understands. You literally cannot leave anything up to assumption. Let's ground this with a familiar example. Think about your morning brew. How does an automated coffee machine actually know how to make it? When you walk up and press a button, it doesn't intuitively know what coffee is, right? It only knows a very strict sequence of commands that a human programmed into its memory.
And this illustrates that sequence perfectly. For a machine, making coffee is essentially just a recipe. Step 1, take 10 grams of powder. 2, add 200 milliliters of water. 3, add 20 grams of sugar. 4, heat it up. And 5, serve. A computer strictly processes sequential commands exactly like this. If you miss a step or mix up the order, the whole machine fails. It only does exactly what it's told.
Section 2. Visualizing the program lifecycle.
Okay, keeping that real-world analogy in our heads, let's transition to the visual system we use to chart these kinds of instructions. Before we write code, we draw using flowcharts. Every basic program has a linear lifecycle, taking a very specific path from the moment it wakes up to the moment it finishes its task. It always begins with a start command. Then it usually takes in some input, like you typing in a number. Next, it performs a process, which is usually a calculation. After that, it gives you an output, like printing an answer on your screen. And finally, it reaches a stop command.
And when you're drawing flowcharts, the shapes actually matter. Think of this as your visual cheat sheet for mapping that lifecycle. An oval is always used to show the start or stop of a program. A parallelogram means you're taking an input or giving an output. A standard rectangle is used for processing, like doing the actual math. And the diamond? Well, this is a super special shape used for making a decision based on a specific condition.
Section 3. Decisions and accumulator loops.
Because, let's face it, programs are rarely just a straight line. Let's look at how that diamond shape acts as a physical fork in the road. A condition evaluates to either true or false. It can never be both. Say we want to find the largest of two numbers, A and B. We give the computer the condition, is A greater than B? If we input 15 for A and 5 for B, the condition is true. So the computer takes the true path and outputs A as the largest. If A was 5 and B was 15, well, that's false. So it takes the alternate path and outputs B. The absolute crucial point here is that the computer can only choose one path.
Now, what if we need a computer to repeat an action? To track this, we use something called an accumulator. This is basically just a placeholder or a variable that bumps up its own value every time a loop runs. You'll often see it written like this: num equals num plus 10. You're taking the current value of the variable, adding 10, and storing that new answer right back into the exact same variable. But remember, an accumulator must always be initialized with a starting value. Otherwise, the computer has no idea what it's supposed to be adding to.
Let's break down the mechanics of that loop step by step. We initialize our starting value at 0. On the first cycle, the computer calculates 0 plus 10, making the new value 10. On cycle 2, the current value is 10, it adds another 10, boom, 20. Cycle 3 updates it to 30. The computer is just constantly updating its own memory. And honestly, this is exactly how a program can count, repeat instructions, or track total sums over time.
Section 4. Writing logic with pseudocode.
So, we've mapped our logic visually, right? Now we bridge the gap to actual typed code. Enter pseudocode. It's exactly what it sounds like, fake code. It's a way to write out your program's logic using simple, plain English instructions. Why do we bother doing this? Because it completely removes the stress of trying to remember complex programming syntax, like semicolons or weird brackets. It lets you focus purely on solving the logical problem at hand.
To see this in action, let's tackle a classic computer science problem, figuring out if a number is a prime number. To do this, we need a special operator called modulo.
Modulo simply returns the remainder of a division. For example, 7 divided by 2 is 3, with a remainder of 1. Because the remainder is 1, the computer instantly knows 2 does not cleanly divide into 7.
Right, so how do we write the pseudocode to find a prime number? Well, a prime number is only cleanly divisible by 1 and itself. So our logic goes like this. Step 1, start a loop at the number 2. Step 2, divide our target number by this loop number. Step 3, check the modulo. If the modulo remainder is 0, it divided cleanly, which means it is definitely not a prime number. If it doesn't divide cleanly, we just increase our loop to 3, then 4, and keep checking.
But check this out. Here is where we get to do some brilliant logic optimization. Let's say we're checking if 36 is a prime number. A standard loop would test every single number from 2 all the way to 35. That's 34 separate processing steps. But mathematically, factors repeat after the square root of a number. So instead of testing all the way up to 35, we only need to test up to the square root of 36, which is 6. We literally just slashed the computer's workload from 34 steps down to just 6 steps. That is the power of optimized logic.
Section 5, Testing through Manual Tracing.
Okay, so you've drawn the flowchart and you've written the pseudocode. Now you have to prove your logic actually works before writing the final program. We do this through manual tracing using an input process output, or IPO table. Basically, you become the computer. You literally plug test values into your flowchart and track them. Let's trace a flowchart meant to find a sum and an average. For input, we feed it 10 and 20. Under process, we write out the math. 10 plus 20 equals our sum of 30. Then, 30 divided by 2 gives our average of 15. Finally, we confirm the output is exactly what we mathematically expect, 30 and 15.
Now, what happens if your manual trace gives you totally the wrong output? Well, our sources really hit the nail on the head with this quote. The purpose of the flowchart is for you to follow the flowchart as it is, not for you to start making changes. If your trace yields nonsense, it means you've successfully exposed a logic error in your own blueprint. You can't just guess what the output should be. You have to track exactly what your diagram tells you it is. And that right there is why manual tracing is an absolute must. It mathematically proves your logic. It flags exact failure points, like maybe branching down a true path when you meant to go down a false path, long before you start writing the actual code. It empowers you to catch your own hidden bugs. Because debugging isn't just about fixing broken code, it's about fixing broken logic.
Understanding all of this, flowcharts and pseudocode, means you've officially unlocked the core language of problem solving. You aren't just a user of technology anymore. You are an architect of logic. You know how to take inputs, process them with accumulators and optimize loops, and manually trace your steps to ensure perfection. So now that you know how to draw the blueprints, what complex problem are you going to build a solution for next? Thanks for joining me on this explainer, and keep building.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming soon.